Hey guys, we're the Top Coders and I'm Felipe. Today we're gonna approach the top k elements in an array problem. In this case, k equals 3. What exactly does top k elements means? Top k elements means that we're looking for the top elements, whatever value of k that is, in an array. So this would be the top 3 elements in an array, the top 3 biggest elements of our array. A quick brute force approach to this problem that will solve it is by actually keeping a max variable and going through every single, oh wow, we actually only have 7 elements. Okay, and we go through every single one of the elements in this array and we compare it with what we have seen so far. So in this case, max equals 10. And then we check it and compare it with 1. 10 so the max, 5, 10 so the max, 42. Oh, we found something bigger. We replace it. Compare it with 1, 42 so the max, 42, 42. We write that on our response array. Remove it from the actual array and go to the next iteration. So we take a look in the empty array and 10 is bigger than nothing, still bigger than 1, bigger than 5, bigger than 1, bigger than 2, bigger than 3. We write 10 down on our response array. Remove it from the array that we have so far and then compare it with the next one. 1 is the biggest so far. Now we see 5. 5 is bigger than 1, so we replace it. Go on to the next element. 1, 5 still bigger, 2, 5 still bigger, 3, 5 still bigger. Write it down in the response array and remove it from our array. Now we have found the top 3 elements. How long is this going to take to run? For every single of the k elements, we're going to have to compare it with every other element. So we're going to have k times n running time. Now, this sounds like a bit too slow for me, doesn't it, for you? We can make this faster. Let's try to make it, how can we make this faster? What if we kept a data structure that only stored the top k elements that we have seen so far and compared it with the smallest element inside of this data structure? Wow! Eureka! There is an actual data structure that does exactly that. We have something called a heap. And this is what we're gonna explore in the next part of the video. And the neat things with heaps is that you have a constant checkup time, in this case for the smallest elements, a logarithmic insertion time, and a logarithmic deletion time. So, we'll attempt to make either k turn into log of k, or n becomes log of n. So with that intuition of us wanting to store only the top elements that we have seen so far, we'll create a heap that does exactly that. And we need to be very careful here since we're going to use a mini heap. Why a mini heap, do you ask? Since we can only compare with the top elements of our set. And this means that we want to find the smallest elements in a very quick time of our top elements. And that way, we might replace it. It's the only element that we care about replacing. Because the bigger elements, we're sure that it's going to stay on its set, at least for the current iteration. And so, creating a mini heap, we got 10 and 1 to 5. We put 10 on top, 5. We put 1 on top, 5, and 10 on the children nodes. And we compare it with the next guy, 42. 42 is greater than 1, so we just replace it. Now, having replaced 1 with 42, 5 goes up, and 42 stays in the bottom, as it's a mini heap. We compare it with 1. 1 is still smaller, so we don't have to do anything. 2 is still smaller, don't have to do anything. 3 is still smaller than 5, don't have to do anything. For every single one of the replacements that we had, it took log k time. And imagining that we had to replace an element every single time in our heap, if the top 3 elements were the last 3 elements of our array, it would take, if they were actually sorted in ascending order, we would have to replace them every single time. As always, we're finding something bigger than what we have so far. So these replacements would take log k time, and the insertions for every element would also take log k time. We can simplify this to 2n log k, big O. And big O is interesting since it's asymptotically, we don't really have to worry about constants. So we just say that we have this running on big O of n log k time. Now, with having thought of that and having heaps in our mind, we can go to the next iteration of our problem, finding something even more optimal. We can think, what if we had everything in the heaps and we just removed out the top element every time? Then how long would that take? Maybe that would work. And we would have a max heap, storing the max elements always on top, and we just have to pop it. Easy, no? Alright, having built up this intuition and our max heap, we're actually going to run through the algorithm. And the algorithm is very simple. We just remove the top element, which is, in this case, 32. We bubble it up, whatever. Another element is. And we do that for every of our k elements. So on the next step, we would remove 10 and put it on our response array. Bubble up number 5. And then we want to remove number 5 and put it on our response array every single time, taking log n time for the k elements. And this would give us k log n times. And this is the optimal algorithm that we know of. As we can clearly see that big O of k log n exists in the big O of n log k. So it runs faster. And this is our optimal algorithm. Thanks for watching, guys. Subscribe to our channel.